Welcome. This talk will present tropical Pacific chlorophyll variability associated with El Niño Southern Oscillation and so in observation and GFDL ESM for simulation. In particular, we found ocean and atmospheric drivers of ion supply, which can drive post-El Niño chlorophyll rebound simulation in the GFDL system model. So let's get started. Here is an example for ENSO-related chlorophyll patterns. Top panels show El Niño events in mature state in boreal winter. When El Niño happens, suppressed ocean upwelling, reduce surface ocean phytoplankton estimate from the satellite ocean color chlorophyll, because the nutrient supply from deep ocean layer is gradually suppressed due to the deeper thermocline than normal state. After that, the bottom panels show the patterns in the El Niño decaying state. It's very interesting that we can see the strong rebound of chlorophyll pattern in the eastern Equatorial Pacific. The discharging sea surface height in the boreal summer after El Niño events can drive the pattern of chlorophyll rebound. So capturing this pattern of chlorophyll rebound in the Earth system model is very important to simulate the marine ecosystem resiliency. So previous generation GFDL ESM2M nicely captured the ENSO-related chlorophyll pattern. For example, negative and positive chlorophyll anomalies throughout the ENSO events. But the ENSO chlorophyll simulation was a bit narrower than observation in the boreal winter, or weaker positive pattern in the boreal summer. The development in new generation of our system model of GFDL for participating in IPCC AR6 report was evaluated to have better fidelity of ENSO simulation compared to previous generation ESM2M. In addition, dynamic land vegetation related dust emission and its atmospheric dust ion delivery are now included to simulate the comprehensive ion cycle for marine ecosystem simulation. So the main motivation of this study is that how about GFDL ESM 4.1 and the unraveling the hidden mechanism behind based on the comparison between the previous and new generation system model in GFDL compared to the observation. Here we show the ENSO chlorophyll patterns based on the Niños 3.4 index. So upper left shows observed patterns of the chlorophyll anomalies, and right panel shows ESM 4.1 simulation. The general patterns in the GFDL ESM 4.1 is closer to observation than ESM2M, as we see previous study. We can see the pattern correlation scale of ENSO chlorophyll patterns in the tropical Pacific region, which shows a better fidelity in the ENSO chlorophyll patterns in the ESM 4.1 throughout the ENSO state. Especially, we can see that post-El Niño chlorophyll rebound can be simulated above the 0.5, while ESM2M was not captured before. There is most significant change in the new generation model that successfully simulates the observed pattern in chlorophyll rebound. Some background in the tropical Pacific should be addressed here. In the tropical Pacific, micronutrient ion is strongly limited since less supply from atmosphere and land. This ion limiting pattern is captured in the ESM 4.1 as well, so that ENSO-driven ion supply can contribute simulation in the post-El Niño chlorophyll rebound. Firstly, we assessed oceanic drivers in ion transport from the Western Pacific and its delivery through the Equatorial undercurrent. So top panels show the ENSO regressed temperature anomalies. When El Nino happens, downwelling Kelvin wave deepens the thermocline. After that, discharging the sea surface height can lead to decaying ENSO El Nino to La Nina states. However, the previous generation ESM2M shows slower ENSO decay that remains warm SST compared to the ESM 4.1. The bottom panels show the ENSO ion patterns, suggesting that the positive ion anomaly is propagated from Western Pacific to the Eastern Pacific through the thermocline, where eastward undercurrent is strongly occurred, which called the Equatorial undercurrent. But this signal is weaker in ESM2M at post-El Niño to reach out the positive ion anomalies at the Eastern Pacific surface. The ESM2M has a bit longer persistency of the ENSO than remaining warm SST anomalies. So surface warming could discharge the ion transport to the Eastern Pacific surface to simulate the chlorophyll rebound. However, this pattern is tempered in the ESM 4.1 because of better ENSO simulation in ESM 4.1 that create for full ion supply through the Equatorial undercurrent. So we can conclude that this oceanic driver is very helpful to simulate the observed pattern in the chlorophyll rebound realistically. And second, we check the aerosol optical thickness, AOT, in the observation. When El Nino happens, the precipitation is increased in the Central Pacific Ocean due to the westerly wind anomalies. At the same time, the reduced water circulation can generate strong subsidence motion in rand area in El Nino events. So that create more atmospheric dust estimated by the aerosol optical thickness based on the satellite record. In GFDL ESM 4.1, increased aerosol optical thickness has been captured in the El Nino events. This is resulting from changing rand soil moisture, wind stress, and vegetation that enhance dust emission from rand to the atmosphere. We assume that this atmospheric dust emission can be another important driver on post-El Nino chlorophyll rebound. So by considering ion deposition based on the interannual variation of dust emission that contained approximately about 3.5% since Baker and Crude 2010. So interannual variation of dust ion depositions were simulated in the ESM 4.1 that can influence on the post-El Nino chlorophyll rebound on the ocean surface as an atmospheric source of ion. So left panels show the dynamic dust ion deposition anomalies, suggesting that the El Nino-driven weakening of water circulation drives land dryness and less soil moisture anomalies that lead to more dust emission and ion deposition on the ocean surface. This can modulate the ENSO-driven ion supply in not only oceanic low, but also in atmospheric low in post-El Nino chlorophyll rebound. So we further integrate the idealized experiment to quantify the atmospheric ion dust deposition effect. Here is an experimental design of ESM 4.1 static dust simulation. So ESM 4.1 and ESM 4.1 static are basically the same. But ESM 4.1 static have the same amount of the long-term mean ion deposition globally. However, we prescribe monthly mean climatology of dust ion deposition, which means the atmospheric dust ion deposition is not varying interannually in the ESM 4.1 static simulation. Here is the results from twin experiment difference between the ESM 4.1 and ESM 4.1 static simulation. As you can see, ion anomalies associated with ENSO are increased throughout the ENSO events. When El Niño happens, ion supply is increased by more dust emission from land due to the weakening of local circulation and less precipitation on land. This turns out positive chlorophyll sensitivity throughout the ENSO state. The right panels show the sensitivity of ion and chlorophyll between the ESM 4.1 and ESM 4.1 static, suggesting that the decreasing ion supply and chlorophyll anomalies are tempered due to the high atmospheric ion supply in boreal winter. In contrast, post-El Niño rebound can be enhanced by high atmospheric ion supply in boreal summer. Especially in boreal spring, atmospheric deposition anomalies are strongest in both observation and simulation that modulate timing of chlorophyll transitions from negative to the positive in spring season. So in conclusion, by comparing previous and current generation Earth system model in GFDL, we suggested that better fidelity of the ENSO-driven marine phytoplankton variabilities, especially post-El Niño chlorophyll rebound, can be simulated by ion trapping in the Western Pacific subsurface and its propagation to Eastern Pacific through the Equatorial undercurrent. In addition, atmospheric driver can play a role in modulating the sensitivity in post-El Niño chlorophyll rebound. This mechanism can be reflected to the future projections for marine ecosystem variability. The change in wind, vegetation, moisture, and dust emission will be very critical to marine ecosystem change through the atmospheric ion supply. So that's it. I will stop here and thank you for your attention.